Okay, we will see some important points in the class 12 physics chapter 4 moving charges and magnetism. Okay, moving charges or currents produces a magnetic field in the surrounding space. That is, moving charges or current produces a magnetic field in the surrounding space. So here this cross means current is going into the plane, and the using your right hand thumb rule you can find the direction of the magnetic field like this. So the here it is coming out of the plane, so the direction of the magnetic field is like this. So this is iron filings again surround the magnet. The arrangement of the iron filing around the wire. Okay, darkened source. Okay, a current or a field, electric or magnetic, emerging out of the plane, the dot, and the current or field going into the plane is a cross. This is the electric field at a distance r from a charge q, you already seen in the other chapter, and this is the force. Force equal to charge into electric field. It is found that obey the, if you have more charges, then it is the superposition. Magnetic field of the several sources is the vector addition of the magnetic field of the individual sources. This is principle of superposition. Magnetic field and this is Lorentz force. So the force on a charge due to electric and magnetic field is given by this Lorentz equation. Force, this is the electrical force due to electric field, and this is force due to the magnetic field, F magnet, F electric, given by this Lorentz. These are the following features. It depends on V and V, charge of the particle, velocity, and okay, you can go through this. In this diagram, the direction of the force for positive and negative charge. You see here, you have to use the right hand rule to find the direction of the force, the magnetic field, the velocity, and the direction of the force. For the positive and the negative charges. Okay. The magnetic force is 0 if the charge is not moving. Only moving charges creates the magnetic field. See, force due to the magnetic field is Q into V cross P. It is the cross product of the velocity and the magnetic field. Q is sin theta. When theta equal to 0, then this force will be 0. There is no force. Similarly, theta equal to 180 also, the force will be 0. Theta is the angle between, okay. So the no force when theta is 0 or 180. Magnetic field, that unit is Tesla, that is the larger unit, and the Gauss is the smaller unit. Okay. This is the magnetic field in Tesla. The for Earth's magnetic field is this, near small power magnet, human nerves, that is smallest. Magnetic force depends on the angle between the conductor and the magnetic field, that is V cross B. Magnetic force on a current carrying conductor. Current carrying of length A, cross section A, length L, cross section A, and the total number of charge carriers N. Okay, this is the magnetic force on a conductor. Okay, ILB, length of the conductor, magnetic field, and current. I is the current. Here current is not a vector in this. Permittivity and permeability. Okay, you can go through this. What is this? The permeability of the medium, not by permeability of the medium. Gravitational force does not depend on the intervention medium. The electromagnetic force depends on the medium between the two charges or magnets. A straight wire on the mass is given, length is given, current is given. It is suspended in the mid-air. The uniform horizontal magnetic field. Okay, what is the magnetic? The magnetic force will keep the wire up against the gravitational force. So magnetic force should be equal to this gravitational force. So then we can find, equating this, we can find how much magnetic field is required to keep the wires in this site. See here, force mgm, mass in kilograms. Okay, current in amperes, and the length of the conducted meters. Note that it have been sufficient to specify the mass per unit length. They have given the total mass per unit length is enough, m by l. We can, using m by l, we can find b. That is what they have given. The entire magnetic is approximately this. Earth's magnetic field is ignored. This is for the positive and the negative charges, a different direction. Okay, the force, the electron, it will be along the minus z axis. For the positive charge, is the plus z axis in this diagram. Motion in a magnetic field. See, when the charge moves in the magnetic field, its velocity doesn't change, but direction can change. So the charge moves perpendicular to the magnetic field here. Okay, perpendicular to the magnetic field, and force acts inwards this here. So this charge moves in a circular manner. Its direction changes, but velocity doesn't change. So the magnetic field doesn't change the velocity of the charged particle. No change in the magnitude of the red is produced, though the direction may change. Particle will describe V is perpendicular to the other. Okay, this now what happens if the charge moves in direction like this? So it has a vertical component and horizontal component. It has a component along B, that is the horizontal component. The component remained unchanged because the theta is 0. VB sin theta. Okay, sin theta is equal to 0 means there is no force acting on this horizontal thing. So it will move unaffected horizontally, but vertically we have already seen this, it will move in a circular thing. So here when moving V is not perpendicular to the vertical component, that will move in a circle. Horizontal component will be unaffected, so it will move straight along the magnetic field. The motion in a plane perpendicular B before is a circular one, thereby producing a elliptical motion. The centrifugal force, if you equate this, the radius of the circle, you can find out this. Okay, and the frequency, angular frequency of the rotation, this Q by M is called specific charge. The independence of the V from energy has important application in the design of the cyclotron. Distance moved along the magnetic field rotation is given by the pitch. This is the pitch between the two rounds. helical motion on the charged particle in the okay. Here in the polar regions like Alaska and northern Canada, we see the colored thing and those Alaska and northern Canada, and the poles, you will see this green and pink lights. Okay, due to the collision of the charged particle converging on the poles. This phenomena is this aurora, whatever is, you can read this. Okay, that is why you see colors at the poles in the polar regions, Alaska and northern Canada. Motion of the combined electric magnetic field, we have velocity selector. In this you can adjust the electric and magnetic field to filter out certain velocity of the charge particle, V equal to E by B. So thus the energy will change 0 when the electric and magnetic fields are balanced. There will be no deflection and the charge particle will come out straight. It does not depend on the type of charge, whether negative or positive. Okay, you can adjust the electric magnetic field to filter out certain velocity charged particles. It's also employed, this principle is employed in the mass spectrometer, a device that separates charged particles. Cyclotron is a machine to accelerate charged particle or ions to high energies. These are D's. Here the period of oscillation, frequency, mass of the charged particle, the cyclotron frequency. The frequency is called, here we have 2 D's and produces magnetic field. That here the source of the origin of the charge. So due to this, magnet takes the circular path, so it is accelerated by connecting to a AC voltage, that is the electric field. By changing the polarity of the disk, this charged particle gets accelerated. Okay, AC voltage accelerates this charged particle. Okay. Biot-Savart law, due to the current element, magnetic field due to the current element, small element, infinitely small element dl. Okay, magnetic field due to this element dl, current I at distance r. Permittivity of the free space or vacuum. This is the comparison between the Coulomb's law and the Biot-Savart law. Okay, similarities. So this magnetic field, that is magnetic field due to the small element dl, magnetic field to this current loop, circular current loop, due to this loop at this point. Okay, dl. Here for this smaller section of this you can consider it is a straight wire. and this is the magnetic field due to that loop. Mu naught I divided by 2r is center of the, that is magnetic field at the center of the loop. Okay, this is the radius of the loop. Current I, this is the constant. The direction of the magnetic field is given by the right hand thumb rule. Okay, now here you see inside the loop the direction is upward, the magnetic field go upward. Outside the loop it is direction is downward, going up and down. This is the current and magnetic field direction. Thumb on the current direction and the curl fingers in the magnetic field direction. See, this magnetic field due to this half circle is half of the one circle. So you can go through this problem. Straight segments do not contribute to the B because they are along the magnetic field direction. And the half magnetic field is half of that of the circular rope. Ampere circuit law. Okay, here for the closed surface B dot dl, okay, equal to I enclosed, mu naught into I enclosed. This is for the enclosed current, I due to enclosed currents within that surface, but B due to enclosed and non-enclosed. It may be this B due to maybe enclosed current, and it may be due to other outside the surface also, outside the closed loop also. Okay, here this is the current carrying conductor, this wire. Inside the wire the magnetic field increases linearly within that wire, but because the current enclosed will increase as we move from the center of the wire to the up to this edge of the wire, the current enclosed will increase, but outside the wire the current enclosed is same. Okay, so outside the wire the field will decrease, but inside the wire the field will increase. This is the outside the wire. Outside the wire it depends on the R, inversely proportional to the R, so field will decrease. But look at this inside the wire. So here you have directly proportional to the R. So this is inside the wire directly proportional. As the distance increases, B will increase inside the wire, but outside the wire is this one. Solenoid. Solenoid is solenoid and toroid are the two pieces which generate magnetic field. Solenoid is a long solenoid. We mean the solenoid length is large as compared to its radius. Okay, it has many turns. That magnetic field is vector sum of the built to all turns. Okay, enamelated wires are used for winding so that turns are insulated from each other. See, field here due to the adjacent turns that cancel out each other. You see here they are in the opposite direction. So field here here and all weak field, so we can ignore. Only field at the center we can consider. Opposite circular loop in both sides. Okay, here this. Here and all weak fields, strong fields at the center, that is at the point P. We see that field at the interior midpoint P is uniform and strong along the axis of the solenoid. So the field is along the axis of the solenoid. The field outside we can is approaches 0. So we shall assume that field outside is 0. The field inside becomes everywhere parallel to the axis. So the solenoid, at the center of the solenoid, the magnetic field, you see this number of turns also, that is turns per unit length. Magnetic field at the center of the solenoid, small m, you see turns per unit length. Okay, small n turns, not total number of turns, it's turns per unit length. Toroid is like a solenoid, but it is bent circular, this like this. Solenoid which has been bent in a circular shape to close itself. This is a toroid, bent to close itself. The magnetic field inside the toroid is constant as magnitude. The toroid is closely wound turns. Okay, this is the magnetic field due to the toroid. Average radius, total number of turns here. Okay, here total number of turns we are taking for this, but for the solenoid and turns per unit length we are taking. See here turns per unit length, but here this is for the solenoid, but here is for the toroid. Stronger magnetic field, the radius of the helix will decrease and the radius will increase in the weaker magnetic field. So we have two solenoids here, and this is how the helical path will look like. Force between the two parallel conductors. So two parallel current carrying conductors. This is the magnetic field. Okay, the conductor B carrying the current IB will experience a sideways force due to the field A, due to the wire A. Magnetic field B is the magnetic field due to wire A. Okay, current carrying wire A, the direction of the force. So now both will have the force equal and opposite. Okay, the parallel currents, similar current, they attract each other. Okay, so they are flowing in the same direction, currents are flowing same direction, they attract each other, but they are flowing in the opposite direction, anti-parallel, they repel each other. Okay, this is important. Same direction, then the conductor will attract each other. If the current is flowing in the opposite direction, the conductors will repel each other. Torque on the current loop. Okay, so we have a magnetic field and you are placing a current carrying loop, current loop, and that, so it will experience a torque. Okay, B is the magnet, this is the length here, and this is A is the width. Length of the wire and the width of this like a rectangular loop. Here the net forces cancels, but there is a torque. There is a torque. Okay. So now this principle is applied in the AC motors also. Now if the current direction changes, then the torque direction will also change, so that it will rotate. Area of the rectangle. M is the magnetic moment. Okay, this principle is applied in AC motors. This is magnetic moment is the current into area. Area is the right hand thumb. Magnetic over number of loops. More than one loop is you have to multiply with the number of loops. N, capital N. Circular current loop as a magnetic dipole. So it will act like a magnetic dipole, current carrying loop. This magnetic field, this above expression is very similar to the expression obtained for the electric field dipole. Okay, the similarity may be seen if you compare this. This is the comparison. Okay, electrostatic field, electrostatic dipole. Similar of the expression obtained earlier for the electric dipole. Magnetic dipole moment of the electron. Electron is revolving around the nucleus. What is the magnetic dipole moment? So electron is revolving, so it constitutes a current. So that is given by E by T. T is the time period of the revolution. Okay, V is the orbital speed. Current due to the electron movement. T is the oscillation period. V is the orbital speed. Here M is the mass of the electron. Angular momentum, magnitude of the angular momentum. Moving coil galvanometer. Okay, this galvanometer used to measure the direction of the current, also the current and voltage. So we have to modify the galvanometer to measure the current and voltage. Depends on the direction of the current, the pointer will move left or right. Okay, depends on the direction of the current. So why we need a shunt resistance? Okay, so to convert this galvanometer as ammeter, we have to need a shunt resistance. If you don't put, then most of the current, because of this high resistance that is consumed by this galvanometer coil. Okay, this is the arrangement to measure the current. How the galvanometer is modified with the shunt resistance to measure the current. And this is how it's modified to measure the voltage. How the galvanometer is modified to measure the voltage. Okay.